Welcome back to part 2 of solving differential equations using finite differencing. So in the last video, I was talking about how we can solve the heat conduction problem using two different boundary conditions, where one of them is the flux boundary conditions like this. So temperature is given at one end, and then the flux is given at the other end. So this time, this is different from that. So this is different in a sense that the boundary condition is not on temperature, is on the derivative of the temperature. So it's a derivative type boundary condition. One is the temperature, the other one is the derivative of temperature. All right, and we discussed that we can use the equation for this from page 83 of the textbook, and we discussed that the equation for the last boundary condition for this one is going to be like this. This is the second order approximation. It's a backward difference of dt dx, right? Because we are sitting on the back end, or at x equal 1, right, then tn plus 1 is going to be the right end, tn is the point before that, and tn minus 1 is another point before this. Okay, and we know that the condition is dt dx equals 0, and because of that, so we set this thing to 0, which means the numerator has to be 0. And that means 3 times the last temperature minus 4 times the one before, and then plus 1 is equal to 0, and that's what I have in the equation right here. So 3 times the last one, so this is the last column of my matrix of equation, minus 4 times that, and plus 1 is the one before that. And the right hand side has to be 0 because the flux is 0 for the right point. Okay, then we're going to go ahead and use matrix package again to solve a system like this. Now I have 10 unknowns, right? T1 through let's say 10 is unknown, right? And then T0 is given, that's 100. So that's what I manually put in here. And after you solve the system with 10 equations, this 10 right-hand side, then you can get these solutions using matrix package. Okay, and then you manually put 100 at the top, then you plot temperature from here to here against the x values from 0 to 1, and that's going to be the curve. So this time we see that temperature is 100 on the left end, and derivative, which is the slope right here. So slope at x equal 1 is 0, right? Slope here, you can look at that. This is completely flattened out, and that means a slope, and slope is 0, and that's what we actually manually hard-coded into the last equation right here. So this means slope equal to 0, right? And that's what we get in the solution. We can do more complex problems. Like in the textbook, it talks about another type boundary conditions, like something like this. Let me see. Well, we can have equation like this or this. Well, actually, these are the same. And this time, the derivative is not equal to 0, right? Let's say dt dx at x equal 1 is a function of t1. Okay? So this time, we discretize this using backward difference as before, right? Exactly like this. So this is going to be the backward difference this is going to be the backward difference version of dt dx. So this is equal to now minus h over k t1 times ta, right? And then we group all the coefficients, right? Like in this case, we can do, let's write this down and see how it's going to be. Okay, so for this, we're going to get, all right, so it's going to be exactly, so the left part is exactly like this, 3n plus 1, right? So it's going to be 3 times n plus 1 minus 4 times tn, right, plus t n minus 1 divided by del x, sorry, divided by 2 del x. So here's 2 del x, okay? that's equal to, and then the right hand side is going to be minus h over k times T1. Let's say T1 is the temperature at the right end. That's going to be Tn plus 1, right? Because the last point is the n plus 1 point. Okay, so that's going to be Tn plus 1 right here, and minus Ta. Okay, so we can group, let's say, well, I have 1 Tn minus 1 Ta plus 1 here, 1 Ta plus 1 here. We can group these two. In other words, we can move this one to the left side and group it with that, and put the coefficients for Tn plus 1, Tn, and Tn minus 1 right here in the last row. Okay, and then what's left over, which is Ta times minus h over k, right? And that's going to be the right-hand side of my equation. It's going to be replacing this 0 right here, and then you get the same system with the last equation changed. And then we can go ahead and solve for the system. So that's how we can even do more complex boundary conditions, right? So we consider 3 types of boundary condition: temperature or boundary condition on the function itself, like temperature, boundary condition on the derivative, like dt dx, and boundary condition on a combination of flux or derivative and the function itself, like here. So there is a flux equal to a function of temperature. So we can do 3 types boundary conditions. Okay, and all we do is we convert them into equations. We put the equations into the big system right here, and then solve for all unknowns at the same time using matrix package. Okay, so this is the last example on section 6. I hope this is useful. Thanks a lot for watching. In the next video, I'll be talking about not chapter 7, because chapter 7 is on regression, so it's a little bit different. So we're going to move on to chapter 8, and then we come back to chapter 7 after we cover chapter 8. Okay, so thanks a lot for watching. Stay tuned for the next section on solving differential equations numerically.